Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we begin to analyze data with a Poisson likelihood. To be more precise, we will do statistical inference for mu, the parameter that identifies that Poisson likelihood. As we already know, to do Bayesian statistical inference, the main two ingredients are 1. The likelihood, and 2. The prior distribution. The first kind of prior that we will consider is a discrete one, okay? But in the future, we will deal with continuous prior distributions for mu. Make sense? Okay, let's begin. So, what we're going to be doing here is we're going to illustrating what's the procedure to analyze data. To be more precise, in this case, in this example, we will consider that we have a single observation coming from a Poisson likelihood, okay? And as I also mentioned a couple of minutes ago, we will start this analysis with discrete prior. Well, so since we're going to be using a Poisson random variable, or to be more precise, the probability mass function of a Poisson random variable as our model for the likelihood. So let's recall what the PMF, the probability mass function for a Poisson random variable, looks like. Okay, so probability mass function for a Poisson. Let me use the following notation. Okay, let me use probability of observing a particular value of the random variable y, and the particular value will be lowercase y, given, and I'm going to be using mu for the parameter that indexes or identifies that Poisson random variable. Okay, so that formula, the PMF, will be given by this, right? Mu to the power y divided by y factorial times e to the negative mu. And the support, right? Y could be 0, 1, 2, so on, right? Okay. Something else from sta360, for instance. Maybe you recall that the expected value for a Poisson random variable is given by mu. And remember, that's just a Greek m, right? Okay. So we are going to be using that PMF, that formula, for our likelihood. Okay? Now, suppose that we believe that there are 4 possible values for that parameter. Okay? For that parameter mu. Okay? Because remember that what we're going to be doing is inference over that parameter mu. Okay? And in Bayesian statistics, we regard parameters as random variables, so they have a probability distribution. And remember, a probability distribution is just a list of possible values along with the corresponding probabilities. Okay? Okay, so suppose that we believe there are only 4 possible values for mu. And let me write those down. How about, let me call the first one mu1. Oops, not what I wanted. So mu1 will be 1, mu sub 2 will be 1.5, mu sub 3, the third possible value, 2, and finally the fourth possible value of mu, 2.5. Okay, so we have our possible values, but we need the corresponding probabilities for each of those values, right? Okay, so furthermore, suppose that we consider that mu2 and mu3 are twice as likely as mu1 and mu4. Okay, so again, suppose that we consider that mu2 and mu3 are twice as likely as mu1 and mu4. Okay, so using that, let's try to use that information and reflect it in our construction of the prior distribution. Okay, prior distribution for our parameter mu. So let me use P1 to refer to the probability that our parameter mu happens to be 1. Okay, and what we said is that we consider that mu2 and mu3 are twice as likely as mu1 and mu4, but we consider that mu1 and mu4 are, well, have the same probability of being the actual value for mu. Okay, so what we would have here is this, right? The probability that mu equals 1 is the same as the probability of mu being equal to 4, and that is some number between 0 and 1 that I'm calling P1. Okay, and then we have a similar situation for these guys. Let me call that guy P2. So we consider that 1.5 and 2 have the same probability of being the what I meant here, right, is the fourth value, which would be 2.5, right? And then these guys, mu2 and mu3, have the same probability of being the actual value for mu, and they have a probability P2. Make sense? Okay, so what we're going to be, and also let me write that down. So P2 is twice as likely as P1. Okay, make sense? Okay, so now what we have to do is use that to come up with the values of P1 and P2, and then we will have our probability distribution, our prior distribution for mu. Okay, so we know from sta360 properties of probability distributions. What we know is that the sum of these probabilities should be equal to 1, right? So we have 1p1 for mu1 and we have 1p1 for mu4. Okay, so we have 2 times p1, and we have 1p2 for mu3, and we have 1p2 for mu2, right? So the sum of those guys must be equal to 1, right? So note that, let me call this guy our third condition. This one here, let me call it condition number 2. This one here, let me call it condition number 1. Okay, so, and this is just from properties of probability distributions, right? So from 3, well, since we're saying that we consider these guys, right, mu2 and mu3 twice as likely as mu1 and mu4, we have this. So wherever we see a p2, we could just plug in 2p1, right? Or the other way around, wherever we see a 2p1, we could substitute by p2, and that's what we're going to be doing. Okay, so from 3, what we have here is, instead of 2p1, we're going to have p2 plus 2p2 must be equal to 1, which means that 3 times p2 must be equal to 1, which implies that p2 must be equal to 1 over 3. Agreed? And then what we have here, right, is that p1 must be just p2 divided by 2, right? So again, from 3, we have that p1 must be p2 divided by 2, which happens to be just, this is the same, note, as 2 over 6. So if we divide that by 2, that's 1 over 6. Make sense? And now what we have is that the probability of mu1, meaning that particular value 1, is 1 over 6, right? The probability of mu4, which is 2.4, 1 over 6, and these guys 2 over 6 and 2 over 6 for mu3, right? So we have a legit probability distribution. Okay, so now we have our 2 ingredients, right? This one here is going to help us model our likelihood, and now we have our prior. So now we can do Bayesian inference for mu. Okay, so but we only have the model here, right? That's a model that we will be using for the likelihood. So suppose that we observe one value, and that value happens to be 2. Okay? So then what we can do, right, to find our likelihood is just this, right? The probability of y, well, random variable y being equal to 2, that particular value given a value of mu, right, is going to be found using that formula that we have up here, right? So let me copy paste this, and we're going to have 4 of these, one for mu1, one for mu2, one for mu3, the other one for mu4. Make sense? So now let me, write it down using numbers. So mu1 happens to be 1. So let me substitute. What we're going to have here is 2, 2, and mu1, as we said, happens to be just 1, right? Let me say that here. Mu happens to be 1, right? So 1, 1. Make sense? Then we're going to be doing the same for mu2, the other possible value for the mean, right? Which is 1.5, and then 2 and 2.5. So let me just modify that. So for the other value is 1.5. So we are going to have here 1.5 and here 1.5. Y equals 2. That's the same, right? Let's do one more. So now we need 2, right? So it's going to be 2 and e to the negative 2, and finally the fourth value would be mu4, which represents 2.5, right? So we have 2.5 here and we have 2.5 here, right? Okay, so now for each of our possible values, mu1, mu2, mu3, and mu4, we have a likelihood, right? Okay, and for each of them, we have a prior probability, right? So recall that there's an easy way of computing the posterior using a table, right? So let's try and construct that table to come up with the posterior distribution for mu. And that way we're going to find out which value of mu has the higher posterior probability, meaning which value has the highest probability of having actually produced our data, in this case our single observation. Okay, so let's construct that table. So first we need mu, then we need our prior, remember, then we need our likelihood, and once we have that, we are basically done, because we know that the next column in our table is the product between prior and likelihood. Right? And then we will be able to find our posterior. Okay? So here we go. We know that mu has 4 possible values. Mu1 is 1, mu2 1.5, and mu3 it's 2, and mu4 2.5. Okay, if you will, let's express that as a fraction, 3 divided by 2, right? Okay, so prior, our prior is going to be, given the conditions that we said we had, right? We said that we considered that these values were equally probable, and these values were equally probable, but that the relationship between them was that mu1 and mu4, right, were not as likely as mu2 and mu3, right? That mu2 and mu3 were twice as likely as these guys. Okay, anyway, so after considering that, we ended up with that probability distribution. Okay, so for mu1 and mu4 we have 1 over 6. Okay, let me go back here. So we have 1 over 6 here, we have 1 over 6 here, and we have 2 over 6 for these guys. These guys are twice as likely. Okay, now likelihood, we have to evaluate those 4 numbers that we have here, right? So it would be 1 square, 1 divided by 2 factorial, that's 2, e to the negative 1. So 1 divided by 2 times e to the negative 1. Okay? Okay. Now next one is going to be 1.5 squared divided by 2 factorial, which is just 2, e to the negative 1.5. So here we go. So it's going to be 1.5 squared divided by 2 times e to the negative 1.5. Agreed? And then the next one, right, is going to be 2, right? So what we are going to be doing is evaluating, just like before, that binomial probability mass function for the Poisson. Okay, and finally we are going to have 2.5, right? So we will have 2.5 squared divided by 2 times e to the negative 2.5. Make sense? And then we will have the product between the second and the third column. So this guy times this guy, right? We do the same for the next one. This guy times this guy, prior times likelihood, prior times likelihood, right? And then we know that when we apply Bayes' theorem, right, we need that numerator, that denominator. The numerator is prior times likelihood, but the denominator is basically the sum of these guys. So we need the sum of that guy, well, of those guys, right, of that column. And finally the posterior distribution is this guy, the numerator, divided by that denominator, which is the sum of all of them. We do the same for each of those guys. Okay, so that's our posterior distribution, right? Using that idea of carrying out those calculations using a table. Okay, so now let's try and do something similar using R, and then let's double check our work. Okay, so first we need our prior, right? That's the first ingredient. So I'm going to using the C function, I'm going to create that vector with 4 entries that contains our prior probabilities, 1/6. Let me write that down as 2/6, 2/6, and 1/6. Okay, so that's our prior. Now our likelihood. Before I do that, so we know that we want to use Poisson as a model for our likelihood, and there's a function called dPois that is going to help you evaluate the distribution or the probability mass function of a Poisson, right? So dPois is here. The entry that you need is the value at which you want to evaluate that probability mass function, and then lambda, right, the parameter of your Poisson. Okay, makes sense? Note that it says that we can use a vector, and you'll see in a minute why that could be useful. So for instance, to evaluate at the first one, right? So what we're saying here is, let's evaluate, right, at 2. Remember that that's what we did. Our observation was 2, right? But the mean was 1 for this guy. We're assuming the first value, right? And then when we did that by hand using that expression, right, that's the likelihood of y equal to 2 given that mu equals 1. That's the first value that we have here. So there you are. Okay, we could do the same with the next value, which is 1.5, right? And then it's going to give you this one. But the thing is, we can do this for a vector. So let's try and do that for a vector. So we want to evaluate the Poisson, the probability mass function of a Poisson at 2, but for 4 different values, namely 1, 1.5, 2, and 2.5, right? Those are the possible values for the mean, mu. Okay? See, we have all these guys. Those are our third column, the likelihood. So let's call that likelihood. Okay? And we know that we need this prior times likelihood, right? And then that gives you that column, the fourth column in our table, and that denominator is just the sum of those products. So we can find that easily using R with the built-in function sum. There we are. That's the sum of these products, and we know that the posterior is just the product of prior times likelihood divided by the sum of all those products. So now let me compare our posterior with the one that we get from R. See? And if you want to round your posterior to say 4 decimal places, you could do it like that, right? And that's it. First entry, this guy, second entry, that guy, so they match. Make sense? So, clearly, from our table and from what we did using R, right, the value with the highest posterior probability is this one, right? Mu 3, which is 2, right? So it seems that based on what we did, based on our analysis, the model that it is more likely to have produced the data is Poisson with a mean of 2. Okay? So, let's quickly summarize what we did here in this video. So the idea was analyzing the parameter of a Poisson, right, using Bayesian perspective, doing this analysis in a Bayesian manner. So what we know is that we need the likelihood and the prior are the main two ingredients to carry out this analysis in a Bayesian manner, right? So the prior, the first kind of prior that we considered was a discrete prior, okay? And once we have that, the prior, and a model for the likelihood, all we have to do is evaluate the function, the model of our likelihood for the observation, right? And we just do what we did before, right? We could do that using a table, right, to create a column with our prior probabilities and then our likelihoods. Then once we have those, it's easy, right? It's just these, it's a product of these guys. So once you have those products, you add them up, and that is going to give you the denominator of Bayes' theorem, right? And then you just do prior times likelihood divided by the sum of all those cross products of prior times likelihood. That gives you your posterior, and you're done. We did it using a table and also using R. Okay, and in R what we saw is that we can evaluate the likelihood using that d Poisson built-in function. Okay, well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.